Picture a chaotic emergency room. A doctor is examining a patient, asking questions, while simultaneously reviewing their written medical history and an illuminated X-ray. An AI system attempting to assist in this diagnosis must be able to process all three formats: verbal symptoms, written text, and visual scans at the exact same time. When an AI successfully cross-references those mixed formats, the results are highly measurable. In complex medical cases, analyzing these combined inputs reduces misdiagnoses by 30%. But most AI systems today suffer from a critical vulnerability known as the modality gap. To process visual data, like a medical scan or a complex chart, traditional models rely on optical character recognition, or OCR, to flatten the image into plain text. That flattening process destroys crucial evidence. Spatial layouts, the precise proportions of a chart, and comparative visual relationships are completely lost when a complex document is stripped down to simple lines of text. Translating the physical world entirely into text creates an AI that functions like an isolated librarian, able to read, but blind to context. To fix this, developers are shifting to a detective model, where the system is trained to link raw photos, audio clips, and text directly to one another. To link those different formats, systems use modality-specific encoders. These act as specialized translation algorithms. For example, vision transformers are used to process images, while architectures like WAV2VEC are used for audio. This animation shows a waveform, a pixel grid, and a text string. The specialized encoders strip away the original file formatting and convert each input into an identical array of numerical values, known as a high-dimensional vector. Those numerical arrays are then plotted onto a 3D geometric grid as distinct coordinate points, creating what we call a shared embedding space. The core rule of this mathematical space is that semantic similarity dictates geometric proximity. If a text document describes an engine failure and an audio clip contains the sound of a stuttering turbine, their coordinates land in the exact same location on the grid. Because those coordinates overlap, a user can type a word into a search bar and accurately retrieve a specific sound or image, entirely bypassing the need for human-generated tags. To prevent the information loss caused by OCR flattening, engineers developed a permanent structural solution called late interaction architecture. This diagram demonstrates how models like ColPoly work. Instead of extracting individual lines of text, the model processes this complex document page, pie chart, sidebar, and all, as a single, unbroken visual grid. By processing the entire grid at once, the AI retains a functional photographic memory of the document's original spatial layout. Retaining that spatial integrity allows the AI to answer complex queries that depend entirely on visual proximity, like knowing that a specific warning label applies to the mechanical diagram printed directly beneath it. Processing multiple sensory inputs at once introduces a new problem: attention bias. This occurs when the AI receives contradictory inputs across different sensory modalities. A specific failure mode happens when a model fixates heavily on a dominant image, like a bright, high-resolution photograph of a machine part, while completely ignoring the critical text warning printed right next to it. There is also knowledge conflict. This is when the AI's pre-trained parametric memory, the data it memorized during its initial training, contradicts the newly retrieved multimodal evidence sitting right in front of it. Until developers can reliably solve these biases and ensure the model prioritizes retrieved evidence over its internal training, these systems cannot be safely deployed in high-stakes environments like healthcare and finance. To manage these conflicts, engineers use agentic RAG orchestration. Instead of a single model guessing the answer, multi-agent systems autonomously debate and prioritize whether a visual chart or a text paragraph best answers the user's query. These systems are also moving past static PDF documents to ingest real-time streaming data. As you can see with this robotic arm assembling electronics, an AI can process live IoT feeds and video streams on a fast-paced manufacturing line. This persistent vector space also provides a foundation for episodic memory. By storing the mathematical coordinates of every past visual and auditory interaction in a dedicated database, the AI can cross-reference what it saw last week with what a user is saying right now. Mapping vision, audio, and text into a single geometric grid resolves the problem of fragmented data. By evaluating these formats as a synchronized stream, the system grounds its reasoning in a multi-sensory understanding that closely mimics the way a human detective pieces together a case.